Okay, thank you very much for the invitation. It's a pleasure to speak here in Lumini about this joint project with Florent Schaffhauser, because actually this collaboration started from a conversation in Lumini. So let me start with an overview of our work. So the objects that we're interested in are quiver moduli spaces. So a quiver is just a directed graph. So we have a finite set of vertices, a finite set of arrows, and head and tail maps, giving the directions of each arrow. And we have a field K. Then associated to this, one can define certain moduli spaces of semi-stable quiver representations over K. So I'll explain how to do this shortly, but so this construction was done by Alistair King using geometric invariant theory. And the two types of actions that we're going to be considering are as follows. So firstly, we're going to consider automorphisms of a quiver. And construct a group of quiver automorphisms. And then look at actions of quiver automorphisms on the moduli space MQ. And an application here will be for Hyperkahler quiver varieties to construct very rich subvarieties as fixed loci of such actions. And the second case is to consider a perfect field and to try and describe the rational points of M by studying the action of the absolute Galois group of K on its K-bar points. Okay. And in this, so in both cases, the goal is to describe the fixed locus. And in fact, we're going to decompose the fixed locus using group cohomology. And give a moduli theoretic interpretation. Okay. So let me begin by explaining what these moduli spaces are. And explaining what a quiver representation is. So a K representation of our quiver Q is given by a K vector space for each vertex in Q, in our quiver Q. And a K linear map for each arrow going from the vector space over the tail of the arrow to the vector space over the head of the arrow. And one can naturally define morphisms between such quiver representations and build an abelian category of quiver representations over K. And since we're interested in moduli spaces, we can fix any discrete invariants. So we can fix the dimension vector of W which is just the dimension of all of these vector spaces here. Okay. So let's fix a dimension vector d. Then if W has dimension d, we can choose an isomorphism between the vector space over vertex v and the standard vector space, and this determines for us a point in the space, so an affine space, which is just I sum over all arrows, and then I take homs from the standard vector spaces over the corresponding vertices. And obviously, these choices of isomorphisms we want to mod out by that. So there's a group that acts on here, which is just a product of general linear groups acting by conjugation. Okay. And so we'd like to construct a moduli space as a quotient of this action. And the way that this is done is by Alistair King. So we could actually just take the ring of invariants here, but it can turn out that we don't have any non-trivial invariants. For example, if the quiver has no oriented cycles. So instead what we do is we linearize the action by using a stability parameter. Which is just a tuple of integers indexed by the vertices of our quiver. And this defines for us a character of our group. So the character group of each GL is Z, and so we get a character like this to the multiplicative group, and we use this to linearize the action. So then we get a moduli space constructed as a GIT quotient. So in fact, we get a rational map to our GIT quotient taken with respect to this character. And it's precisely defined on the open subset of GIT semi-stable points. And I'm going to call this MQD theta semi-stable, so our moduli space of theta semi-stable quiver representations of dimension vector D. And it's a moduli space in the sense that it co-represents the corresponding moduli functor, and its geometric points are what we expect. So that is, they are S-equivalence classes of semi-stable representations. So let me explain what I mean by semi-stable representations. So a K representation W of Q is theta semi-stable if for all proper non-zero subrepresentations we have that the theta slope of the subrepresentation is less than or equal to the theta slope of the representation itself, where, so for semi-stability we want less than or equal to, and for stability we want less than. And what is the definition of this theta slope? So you just sum over the vertices in V, and then take the sort of a weighted sum of dimension vectors and then divide by the unweighted sum of the dimension vectors. Okay. So in fact, because we're not necessarily going to assume that K is algebraically closed, we need to also make a definition of geometric stability. So we say that W is theta geometrically stable if for all field extensions the L representation of Q is theta stable. In fact, this is equivalent to just checking for L being the algebraic closure of K. And so we don't need to define theta geometrically semi-stable because theta geometric semi-stability is equivalent to semi-stability by existence and uniqueness of the Harden-Arrowsine infiltration. So let me make two quick remarks. So firstly, the open set of semi-stable representations. So the set of semi-stable representations is open, and the same for geometrically stable. And by a Hilbert-Mumford type criterion, these correspond with the GIT notions of semi-stability. And secondly, if I have a geometrically stable representation, then its automorphism group is GM, a bit like how stable vector bundles have automorphism group GM. And if you look at the stabilizer for the action of our group GQD on this element, then it's a special subgroup of G, namely it's what we're going to call delta. So it's a diagonally embedded copy of GM. Okay, so this construction was given by King, I mean, for an algebraically closed field, but then you just have to make the appropriate modifications when you're not working over an algebraically closed field. And so let me now explain what I mean by a Quiver automorphism, as in here. So in fact, in our paper, we considered two types of Quiver automorphisms. So either Quiver automorphisms which respect the arrow direction or which reverse the arrow direction. But for simplicity today, I'm just going to talk about the first one. And we call these covariant Quiver automorphisms. So a Quiver automorphism which we write like this, is given by an automorphism of the vertex set and an automorphism of the arrow set. Such that these commute with the head and tail maps. Okay, I'm probably going to stop writing the A and the V from now on, but it's usually clear which one I mean. And then we can construct a group of Quiver automorphisms. This is just a finite group. So let me just remark, as I said orally, that one can also study and define contravariant Quiver automorphisms. But for simplicity, I'm going to ignore this picture in this talk. And in fact, Matthew Young studied contravariant Quiver involutions in order to define orientable Donaldson-Thomas invariants. For quivers. And in fact, I think his motivation was from counting BPS states in physics. Okay, so given such an automorphism sigma, so I'm going to always assume I'm in this covariant case, we get an induced functor on the category of K representations of Q, which, so if we have a representation W, it just sends it to the, so I replace, over the vertex V, I put the vector space from sigma V. And the same for the arrows. Okay. And obviously the dimension changes in this. So we have that the dimension of sigma of W is now the dimension of the vector space over sigma V at each V. So we can just write this as sigma, the dimension of W. Okay. And so if we want to get any sort of actions on our moduli spaces, it's pretty clear that we need to assume that sigma is respecting this dimension vector. So we now assume that we have a subgroup of Quiver automorphisms. So this actually gives us greater flexibility. And we assume that our dimension vector D is sigma compatible, by which I mean that sigma of D is equal to D for all sigma in my subgroup. And we're shortly going to see as well that we need to assume our stability parameter is theta compatible. And in this case, it actually means the same thing. But if we were in the contravariant setting, there would be a sign creeping in here. Okay. Okay, so let's define the action on the moduli space. So using this functor, we can define sigma actions on rep QD, our affine space, and our reductive group GQD. And these are compatible with the action of G on rep QD. So these are compatible in the sense that for every sigma in our group, if we act, so if we take G and then act on some element phi of rep, then this is the same as acting by sigma on G and then using the GQ action on the action of sigma on phi. Okay. And the fact that we chose theta to be sigma compatible means that the action preserves the semi-stable sets. And so we get an induced action on the moduli space. And also the open subvariety of this given by geometrically stable Quiver representations. Okay. And we're interested in understanding the fixed locus of this. So if we, in fact, look at the fixed locus for these two actions, then we see that the fixed locus here preserves the fixed locus here. And so we can take the GIT quotient, and in fact, there is a morphism going from the GIT quotient for the fixed subgroups to the fixed locus in the moduli space. So the construction of this map is just using the universal property of the GIT quotient. The only hard thing is to show that on this fixed locus, the semi-stability for the smaller group, the fixed group, is the same as the semi-stability for G. Okay. And let me make a remark that, two things. So firstly, this variety here is actually also a moduli space for Quiver representations, and namely representations of a quotient quiver. And secondly, that this map is, in general, even if you're working over the complex numbers, neither surjective or injective. And we have examples of both, actually. But when we move to the Galois setting, which I'm about to do now, we'll see that always the analog of this map is going to be injective. Okay, so let me describe the Galois actions. So I'm going to assume throughout that K is perfect. And I look at the action of the Galois group of K bar over K acting on the K bar points of this moduli space. So then the fixed locus is the set of rational points. Okay. And we can see, again, this Galois action as being induced by actions on rep QD and GQD. well, the k-bar points of these spaces. Okay. So then we have an analog of this proposition here. Whereas now we have that we have an injective map. And I'll explain in a second why we restrict to geometrically stable points. So why is it, firstly, so, oh sorry, I wanted to call this F as well, so F Galois. So why is this an analog of the map here? Well, this we can just think of as being the fixed points for the Galois action. And again, here we can think of these as being the Galois fixed k-bar points, and the same here. And so let me explain why it's injective and why we restrict to theta geometrically stable. So the reason for restricting to geometrically stable representations is this point here, that we know that the stabilizer is always this subgroup delta. And then we describe the non-empty fibers in terms of Galois cohomology. And to show that this is actually injective, we use Hilbert's 90th theorem. So remember, delta is just the multiplicative group. Okay. But in general, this map isn't surjective. So it is if K is algebraically closed. And the idea was to try and understand what are the other rational points. So what are the rational points of our moduli space that don't come from K representations? So to understand the points which don't come from K representations, we introduce a type map. Which sort of classifies the different points in our moduli space. And it goes to the Brauer group of K. Okay. And the fiber over the trivial class in the Brauer group is precisely the image of this F Galois. So, yeah. So let me explain the idea of the construction of T, because again, actually the second fact just follows from using Hilbert's 90th, but now for general linear groups. So the idea is to use the fact that we've restricted to the geometrically stable locus. And so if we look at the stack, so sorry, this M is different from this M. So this is the stack. So it's a quotient stack with coarse moduli space given by this moduli space here. And this is a GM job by the second point in this remark here. And then if I have a k rational point here, then I can just pull this GM gerb back, and I get a GM gerb over k, which is precisely an element in the Brauer group. So, of this moduli space. So it'll be important for the rest of the story, actually, that I explain that this map actually factors via the connecting homomorphism. So I have a short exact sequence. So delta is a subgroup of G, and then it includes into G, and then I can take the quotient. And associated to this short exact sequence, I have a connecting homomorphism. And to see this, I mean, in fact, so an element here is just given by a principal bundle for this group, and then you use the fact that the GIT quotient on the geometrically stable locus is precisely a principal bundle for this group. And so in particular, if we have something in the image of the type map, so if you have a Brauer class in the image of the type map, then it's the image of a one cycle with values in this group one cocycle, which I write as alpha bar. And so you can just naively think of this as being a collection of elements in, so alpha bar tau in this group. And then if you choose any lifts of these, to G, well, okay, you should make sure that you take for the trivial element, the trivial element. So if you choose a lift, then this defines a twisted Galois action. So an alpha twisted. On the affine space rep. And on the group GQD. And then you can construct a alpha twisted version of F Galois. Well, okay, sorry. Yeah. Well, now I take the fixed points for the alpha twisted action. And then again, I just take, so this is just the set quotient here. By the action of the alpha twisted fixed points here. And in fact, these two alpha twisted actions induce the original Galois action on our moduli space. So this also goes to M our moduli space. And okay. So then using this, we can describe all of the rational points. So we have a decomposition of the rational points of the geometrically stable part of our moduli space, indexed by classes in the image of the type map. And so again, you can show that these maps F alpha Galois are injective, and that the image is precisely the pre-image of the class alpha under the type map. Okay, so this isn't entirely satisfactory because we would like to understand what these points are. And so we give a moduli theoretic description which now, rather than thinking of the Brauer group as classifying GM gerbs on K, we're going to think of it as classifying central division algebras over K. So then each class alpha in here, as I was writing it before, corresponds to some division algebra D. So, and by Galois descent, for this twisted action, we can construct new K varieties whose K points are precisely the points up here to the left and to the right. Okay. Okay. And then we prove a slightly more satisfactory description of the rational points. Which is that so now if I write it as D, a division algebra in the image of the type map. Oh, and I forgot to mention something. So actually, D lies in the image of the type map. A necessary condition for this is that actually the degree of D, so that's the square root of the dimension of D, divides dimension vector D. Okay. And then we can interpret this set here as the set of theta geometrically stable DD dimensional representations of Q over the division algebra D up to isomorphism. So, I mean, I hope it's clear what I mean by a quiver representation over D. So, okay, yeah, I mean, you can just do linear algebra just as well with division algebras as you can with vector fields, with fields, sorry. Okay. Oh yes, I wanted to explain one example, and in fact this was really the example that we were interested in at the beginning, but then we realized that because the theory is so simple, you can do it for basically any perfect field. So, and that's when we take K to be the reals. So then in this case, we have, so the Galois group, so we just have identity and complex conjugation. And the Brauer group of R is, so it's there's just two division algebras which are central over R. So the reals and the quaternions. And then we see that the real points of this moduli space are either real representations of Q or quaternionic representations of Q. And the latter only occurs if the degree of the quaternion, so that's 2, divides the dimension vector d. And so, for example, for finite fields whose Brauer group is trivial, you just get that there's only the rational points are just coming from actually representations over that finite field. Okay, so let me not explain the decomposition for Quiver automorphisms, but instead explain the application, because the decomposition is slightly more complicated for groups of Quiver automorphisms because we don't have Hilbert's 90th. So I think I sort of suppressed it slightly, but Hilbert's 90th was used in 2 places. So firstly here, to show that F Galois was injective, and then secondly here for this equality. And so essentially we do have a decomposition, but it's much more complicated. And we also interpret the elements in this fixed locus as being equivariant Quiver representations. Okay. So let me explain an application for actions on Quiver varieties on which are Hyperkahler. So there's quite a natural way to get a Hyperkahler Quiver variety associated to a quiver, and that's we take our quiver and double it. So what this means is that I add in some extra arrows, and what I add is for each arrow in Q, we add an arrow in the opposite direction. Okay. So then, if we look now at the space rep Q bar D, oh, and I should have said, now my field is the complex numbers. Okay. So if we look at this affine space now, then what we've done is we had a bunch of matrices, and we've added in or linear maps, and we have linear maps going in the opposite direction. So this we can just think of as being the cotangent space to rep QD, so the undoubled quiver. And this thing here was just some complex vector space. And so then naturally we can identify this with a quaternionic vector space. And then in particular this has, so it's an algebraic symplectic thing as the cotangent bundle of some variety, but it's also Hyperkahler with, so where now I mean Hyperkahler in the non-compact sense, obviously. So we have 3 complex structures. So I, J, and K satisfying the quaternionic relations and a Hyperkahler metric. Okay. So then we can look at our group GQD acting on this. So GQD is the same as GQ bar D because the vertices haven't changed. And there's a algebraic moment map for this action going to the Coley algebra of this group. So this is a algebraic map which is equivariant with respect to this action and lifts the infinitesimal action. And we can construct an algebraic symplectic reduction using this algebraic moment map, which in fact turns out to be a Hyperkahler reduction. So if we take an element in our Coley algebra which is fixed by the coadjoint action, then because mu is equivariant, there's an action of G on the fiber. And we can just take the GIT quotient now. Let me call this X. And again, we can use some character of our group to take this GIT quotient. So this is naturally sitting inside the moduli space of semi-stable representations for the double quiver. And if, for example, semi-stability is equal to stability on this fiber, I should say that I'm interpreting, well, I'm really thinking of semi-stability for the group G quotiented by delta, which acts trivially everywhere. Okay, so then X is smooth, and in fact Hyperkahler, where the Hyperkahler structure is coming from the Hyperkahler structure on rep Q bar D. So I said that you could realize this as actually a Hyperkahler reduction for the maximal compact group in GQD. Okay, so then let me, in the final few minutes, tell you what a brane is. So in a Hyperkahler manifold, so we've got three complex structures and, well, three Kahler structures and a Hyperkahler metric. A brane is a submanifold that is either holomorphic or symplectic with respect to each of the three Kahler structures. Okay. And in fact, there are four types of branes. So you have hyperholomorphic, which is, oh, I forgot to. Right, so these we call B branes. Oh, sorry, Lagrangian here. Yeah. And these we call A branes. And branes in Nakajima quiver varieties were already studied by Franco, Jardim, and Marchesi, but they didn't consider branes coming from quiver involutions. But they considered things like complex conjugation. And now we can add to this branes coming from quiver automorphisms. So this is again with my cohomology. So we show that, so if sigma is an involution, and you have to assume it behaves well with respect to this sort of double arrow situation, and we make all choices compatible. So theta d and eta are all compatible, then if x is smooth and Hyperkahler, then we describe the fixed locus as, so firstly, it's a BBB brane slash, or respectively BAA brane if sigma preserves the arrow set or sigma sends, or sigma sends the arrow set to the opposite arrow set. And if we also combine with complex conjugation tau, then we get a ABA brane in the first case, and the last remaining case, so an AAB brane, if these two conditions hold. Okay, so I should stop here. Thank you very much.
Thank you. Are there any questions?
No? Yes, you explain one restriction on the possible types that appear. Is this the only condition? Or?
Yeah, that's a really interesting question. This is a consequence, but it doesn't necessarily mean that we see those ones. I mean, so it's just a one-way implication, and I think that's a very interesting question, but we haven't looked at this to try and understand exactly when. I mean, because, I mean, of course, if you didn't have a stability condition, it would be clear, but determining whether there's, for example, a quaternionic representation that's stable with respect to some theta is a hard question. I don't know how to answer that.
There are some pure symmetry relations between some Nakajima Quiver varieties, like symplectic duality, which is supposed to act on this BBB brane or ABA branes. So do you know some example where you should know what should be the mirror of your examples?
No, I don't, but there are some interesting conjectures on this in sort of like the Higgs bundle case, actually, and I assume that it's the same sort of thing, that you expect the joule of a certain brane to be another brane, but I would be interested to talk to you about that, but yeah.
Okay, now let me ask a question. Is it the only kind of branes you know, or so is that the construction of all branes?
Oh no, I think you can get branes from many different ways. I mean, this is not it's just that you can get all four possibilities from these techniques. I mean, in fact, you can also do it, if sigma isn't an involution, you can construct BBB branes from larger groups, but so I think there are more techniques involved to get branes than just these.
Other questions? So if not, let's thank